Forces in Motion, Chapter 10. This relates to the second half of exercise 10F. There are two pulleys systems you need to get used to. This is the second one. It's very similar to the first one, except you have a pulley with a weight hanging down, clearly pulling on it, on the system due to gravity. But the second weight is not just hanging down, it's resting on a surface which is almost certainly rough. So it's similar but not identical. The difficulty with the pulleys questions tends not to be the initial setup, it tends to be the final part of the question where this thing falls down, hits the ground, what happens to this item after that has hit the ground, as it slows down, the total distance it travels and so on. But we'll break it down like we did the first one, and then we'll see how we go with the final question, the final bit of it. This is example 14. I'm just going to add a few little things to example 14 to help you with one or two of the later questions. Okay, in this example we have two particles A and B. There's A, there's B. This one is 0.4 kilograms, so let's put my arrow in there. 0.4 G, it's a force arrow obviously. If we have a force arrow downwards, then we must have a normal going upwards, as this object clearly isn't falling through the table or whatever it is. It's a light inextensible string, so therefore the tension pulling that up and the tension pulling that way and the tension pulling against the pulley that way and that way, all of these are the same. They are T. What else have we got? This distance here is 4.5, and if this is the ground, clearly not to scale, then this distance here, it tells me, is 0.5 meters. We have a frictional force acting on A, going backwards obviously, because if this is pulling this way, the whole thing is moving that way, so friction has to work in the opposite direction, and the magnitude of that frictional force is 0.08 times G times gravity. You often get questions where various forces other than just gravity are given relative to gravity. Unless it specifies, it's up to you whether you convert that into 9.8 or whether you just leave it in terms of G. B is 0.8 kilograms, so we need an arrow coming down here, which is 0.8 G. And the whole thing is moving that way. I gather physicists put an arrow around the pulley to show that's where it's working. Mathematicians would tend to put an arrow here and an arrow here. It doesn't actually matter, as long as somewhere on your diagram you can see that the system is accelerating that way. Okay, the first part of the question is to work out the acceleration of the system, and I guess the clue's in the word system. We're going to treat the system as a whole. We're going to look at all the forces pulling it this way, all the forces pulling it that way, take them away from each other, we'll get our resultant force. Once we have our resultant force, we can equate that to the mass times acceleration, therefore work out the acceleration. So let's do that. We're going to work out the acceleration. I'm leaving lots of space over here because the third and fourth parts of this get quite involved. Okay, so what forces have I got pulling it that way? The only thing moving the system that way is the weight of B. So in a positive direction, I've got 0.8 times G pulling that way. What forces have I got slowing the whole system down or pushing them that way? The only thing I've got, assuming there's no friction, assuming this is a smooth pulley, the only thing I've got is the friction on A, and that is working that way, so it's minus 0.08 G. So there's my forces, that's the total of that is my resultant force, and the resultant force is making this total mass of 1.2 times 1.2 kilograms. Accelerate at A. So just rearranging, 0.8 g minus 0.08 g is 0.72 g divided by 1.2 will give us acceleration. I'm going to work it out to a couple of decimal places. You can leave it in terms of g if you want. 0.72 times 9.8 divided by 1.2 gives me acceleration of 5.88 meters per second. So the whole thing is accelerating at 5.88 meters per second until, of course, this thing hits the ground, more of which later on. I think in the textbook they rounded off to 1 decimal place or 2 significant figures. Unless they specify, it doesn't really matter. 2 decimal places is always a good rule of thumb. Okay, how long does it take B to get to the floor? That's the next thing we need to consider. So we're looking for time. We want to find the time it takes. We know what the acceleration is. So this is for part B. The acceleration is 5.88 meters per second squared. We know the distance is 0.5 meters. And it tells us in the question that the system is released from rest. So at the start of this, B has an initial velocity of 0. So therefore we need an equation that links S, U, A and T. I'm going to use S equals UT plus a half AT squared. So 0.5 equals U times T. That's 0. That's a positive direction, obviously. So half times acceleration 5.88 times by T squared. A little bit of rearranging. 0.5 divided by 0.5 times 5.88 gives me 0.17. So T is the square root of that. Square root of that answer is 0.4. Whoops. T is 0.41 seconds. I should really have written that down. 0.17. So T is 0.41 seconds. That's the time it takes this to reach the ground. The other thing I'm going to work out before I get on to the tricky last bit, which doesn't ask me in the example, but I'm going to do it. Let's work out the tension in the rope. Now, because it's inextensible, because there's no friction around the pulley, the tension along the top here going either way is the same as the tension here. So I can either choose this one or choose that one. Either way, I should get the same answer. I'm going to do both to show that in fact you do get the same answer. So let's start with B, the tension in B. Let's have a look at what's going on. It's accelerating downwards at 5.88. I've got a force pulling it down, 0.8 G. I've got a force, tension, pulling it up. Well, I've got all the information I need. Let's take that as positive. So I'm going to write my force equation, F equals ma. So resultant force, I've got 0.8 G pulling it down, T pulling it up, and that's minus T because it's going the opposite way to our positive. So that's the resultant force equals the mass times the acceleration, which I know is 5.88. So rearrange that. And I get the tension is 0.8 G, take away 0.8 times 5.88. 0.8 times 9.8, that's 0.8 G, take away 0.8 times 5.88. That gives me a tension of 3.14, let's say 3.14 newtons, rounded off to 2 decimal places, 3 significant figures. Okay, let's find out the tension in this rope here. Let's just to show you that it doesn't matter which one you choose. If you want to work out the tension, you'll get the same answer. So let's do the tension in the rope at A. So again, looking at this whole mechanism here, that way is positive. It's moving this way, so I'm going to take that as the positive. The only force I've got acting this way on it is the tension. There it is. I've got a force pulling backwards. That's the friction minus 0.08 G. Those are the only forces I've got operating in that direction. And that's got to equal mass. The mass is 0.4 times acceleration. The accelerating the particle, the object is moving, accelerating at 5.88 meters per second squared. 5.88. So T equals 0.4 times 5.88 added on to that, and hopefully that will give us 3.14. Well, let's see. 0.4 times by 5.88. Add on the 0.08 times 9.8 gives us 3.136 or 3.14, which was the same as what I got down here. All right, the last part of the example was to work out the total distance that this thing moves. Now there's two things going on here. The first bit of movement is as B is dropping. So B falls a half a meter. During that half meter, that will move half a meter that way. Once B hits the floor, there is no longer any tension in the rope. A is moving that way. It reaches a speed, a top speed, which we'll have to work out in a minute. And then because there's no more accelerating force acting on it, the tension in the rope has gone because B has hit the floor. The only thing slowing it down is this one. The first part of the journey, as B hits the floor, is quite easy. It just goes half a meter that way. It's the second half where we need to work out the distance. We need to work out the distance. We don't know as yet what the deceleration is. As yet, I don't know what its initial velocity is at this point, but I know, of course, the final velocity we know because it stops. The initial velocity of this at this point, I don't know what that is either. T, I don't think T is relevant in this case. I don't want to work it out. I'm sure there's ways you could work out T and use that to solve it. But there's two bits of information here that I need. The initial velocity of A at this point, as it starts to slow down, is the same as the final velocity of this when it hits the floor. So what I'm going to do is to work out the velocity of this when it hits the floor. I've got most of my information here. So let's work out the final velocity of this when it hits the floor, and that would be the same as the initial velocity of this at this point. Okay, so we're now dealing in B. It's got a distance of 0.5 meters, so S is 0.5. Its initial velocity was 0. Its acceleration is 5.88. We want to work out V. So I've got all the information I need here really. V squared is U squared plus 2AS. That's what I'm going to use. U is 0, so V squared is 2 times 5.88 times 0.5. So V is the square root of whatever that is. Well, 2 times 0.5 is 1. So V is the square root of 5.88, which is square root of 5.88, 2.42 meters per second. So this is doing 2.42 meters per second when it hits the ground. So this is traveling at 2.42 meters per second when that hits the ground, when the rope stops having any tension in it. So that's the bit I need to work out the second half of the journey for this. So U is whatever V was here, 2.42 meters per second. I want to work out the distance it travelled. Now, I need to work out the acceleration, and I can do that using F equals ma. The only force acting on this is now the frictional force. We know the mass, so we can therefore work out the deceleration. Rearranging this, A is the force, which is obviously working backwards, divided by the mass, which is 0.4. So the acceleration, deceleration, clearly it's slowing down. It's 0.08 times 9.8 divided by 0.4, which is minus 1.96 meters per second squared. Minus 1.96 meters per second squared. Right. I want to find S. I've got A, I've got V, I've got U, not interested in T. The only equation I can think, formula I can think of rather is V squared is U squared plus 2AS again. So 0 equals 2.42 squared plus 2 times minus, 1.96 times by the distance. So the distance, so the displacement is going to be minus 2.42 squared divided by minus 3.92. 2.42 squared divided by 3.92 gives me 1.49 meters. So once A has travelled its half a metre and that hits the floor, A then travels a further 1.49 metres. Clearly this 4.5 metres is plenty big enough for it to slow down. A is never going to hit the pulley, so the total distance travelled, the total distance is the 1.49, which is the second half of the journey, plus the 0.5 metres for the first half of the journey, giving me 1.99 metres to 2 decimal places. A little bit complicated, but as ever with your SUVAT, write down everything you know, write down what you're trying to find. If there's forces involved, you'll also need an F equals ma. So along with your SUVAT equations, you'll need an F equals ma. A little bit complicated, but this type of question, the last part of this, does often appear in exam questions. Practice them lots.